this video is about designing a sequencer for the DIY drum machine. So here's the basics of the sequencer circuit, designing a sequencer for the DIY drum machine with the various voices that we have. So basically this all centers around a CD4017, which is a decade counter. So the CD4017, it's basically a 16-pin chip that counts to 10, and you could use it at 12 volts. And so the way the chip is designed, pin 16 is VCC, pin 8 is ground, and the outputs are labeled, based on the sequence that they go in. So, it's unfortunately, this chip is designed so that they're not straight. So it's 5102-673 ground, and then 8, 4, and 9. The pin 15 is the reset pin. Pin 14 is the clock. There's also a pin 13, clock enable, and that has to go to ground. And so the way it's wired is that the input is coming in from a low frequency oscillator, and that's a 555 timer in my case. That's adjustable. The clock is connected to ground so that it's pulled low when it's not on. And same thing with the reset signal. The reset signal, since I'm doing an 8-step sequence, I'm basically connecting the outputs to pin 0 is the first output, pin 1 is the second output, etc., etc. And so it goes all the way to 7. 7 is the highest one, 0 through 7. And then when it goes to 8, I have the 8, when it goes high, circled back and connected to reset. So it resets to the first step of the sequence. So now, based on our design, the outputs of the pins start out this way. Let's zoom in on a little bit. So basically the outputs of the pins are as follows. You connect the outputs. First, you need some kind of indicator. So I used LED lights. You could do them directly through a high-value resistor, or you could have NPN transistors driving them. Either way, this is the sequence, the way the LED lights are driven for the sequence. Also, off of the outputs now, we're going to talk about the final design, both for the gates and the control voltages. So for the gates, it's very easy. Each individual output is connected to a switch. Those switches, based on turning on a drum voice for each, for various steps, you turn this on or off on manually. And then the outputs, since these can source current, you want to put them through through diodes here. So the output of the diodes is all connected. And then the output of all of that is going to this NPN transistor-based AND gate. That transistor-based AND gate, because the outputs at each individual step are always constantly on, if all the switches are on, then you never really get a gate pulse. There's never a time when this is completely off. And so you need a pulse in order to create a gate. You need the signal to go high and low. You can't just have it go high and stay high for a large amount of time, because it'll never trigger the gate to trigger converter. So the way to do that is, because the outputs of these gates are always high. Let me draw a little graph here. And we're ANDing this with the clock, which goes high and low. And when you put those two together through this transistor, your output signal is like this. So you actually trigger the gate to trigger converter. And so this will function as the gates for each individual step of the sequence. So this is the design of a sequencer. So the way the sequencer circuit is designed is using some form of a clock and some form of a counter. And so the clock sets the pace, and the counter advances the count each individual step. So here I have on the left side a 555 timer to set up as a low frequency oscillator to set the pace. And I have here a CD4017 CMOS decade counter. It counts to 10, but I have it set up so that it is resetting after 4. So just to demonstrate. So this is a 4-step sequencer here. And so I have the resistors coming from output 0, 1, 2, and 3 going to these LEDs. But at the same time, the way the gate of this of the sequencer signal works is that you can't just attach the outputs directly to the voices of whatever you're triggering, because they can these outputs can sync circuit as well as source circuit current. And so what happens is you have to connect them basically through diodes to one side, and then at each individual step as it advances, the signal from the diode from the same point of all the outputs of the diodes will be going to trigger the sound voice that we want to trigger. So the problem with this type of circuit is that, and I'll demonstrate it right now. So I have here the LFO blinking away, and you can see the LEDs being turned on sequentially, and the diodes are all going to that one point. And so you're thinking that it's going to trigger, but if you look at the oscilloscope signal, it's not seeing pulses. The oscilloscope signal is just a flat line at 12 volts. And the only way to trigger a signal is it's got to have a pulse. It can't just be a flat 12 volt signal or 5 volts or whatever voltage you're using. It's got to go down at some point. Otherwise, it'll never trigger an envelope. It'll never trigger the gate to trigger converter. And so it'll just always stay on. So how do we make this happen? And the way I've figured out to do it is with transistors. So let's see how to fix this. So now I've changed the sequencer circuit. It's the same way it was before, with the CD4017, the 4 LEDs through resistors, and the diodes all going to the same point. But now, in order to provide an actual gate pulse for this, I've wired the output of the combined diode output through a 5K resistor to the base of an NPN transistor. So the base of that NPN transistor turns on and off with the clock. That's the base of the transistor. I'm sorry, it's not going to the resistor is going to the base, but that is the output of the clock. And the output of the diodes, which is always on, as we saw in the previous clip, is going to the collector of that transistor. And so basically this transistor is set up as an emitter follower and functions kind of like an AND gate. for the signal. And so the output of that signal is going into my oscilloscope, and let me turn it on and see and compare it to the previous one. So here it is. The LFO on the left is oscillating at a slow pace. It's providing a square wave, and the sequence is stepping through. The LEDs are going on sequentially, 1 through 4. The diode output is going to the collector of the transistor, and the clock, which actually does turn off in between, is turning that transistor on and off. And what's coming out of the emitter is a signal that looks like this. Rather than being constantly on or off, rather than be constantly on, it is going on and off according to the transistor being turned on by the clock. And so what we have with that is a nice wave, a nice square wave that will actually trigger each individual voice at each individual step. So that is the essence of the sequencer, to provide a gating signal. Now, also off of these very same outputs, you want to, if you want to use control voltage for the circuit. So control voltage, as I discussed in the previous video, is basically adjusts the voltage of whatever signal you're sending out in order to control it. This is more for voltage-controlled oscillators, but you can be used in voltage-controlled areas of the drum circuit that I've shown in a previous video. But basically, the way this works is each individual output is also in parallel connected, in addition to the gates, is connected through various potentiometers that are configured as voltage dividers. So this is the output, pin 3 of the potentiometer. The ground is usually the ground is usually the pin 1, and the center pin, which is the output of the potentiometer, also goes through, all of these also go through a set of diodes that are connected together so that there's no backflow of current here and in the sourcing here. And what you have to decide here is your control voltage scale, right? So the outputs of these will, based on whatever potentiometer settings you have, will give you outputs of 0 to 12 volts. And so often control voltage situations don't require 0 to 12 volts. Conventional sequencers use 0 to 5 volts. And so to get it down to about 0 to 5 volts, I just did it the basic easy way, just put it through a voltage divider with 100K and 100K. And so that gets you down to 0 to 6 volts after the voltage drop on the diodes. It's basically 0 to 5.09 volts. So it's pretty close enough to a 0 to 5 volt control voltage circuit. And these are your control voltages. So these are connected to your CV inputs of the various drum voices that you've created. The other important aspect of any sequencer circuit is, now I've made a mess here, is adding control voltage. So when you have a sequence where you have aspects on the voices that are controlled by various voltages, the other thing you have to take off of the outputs of the CD4017 chip here is outputs to potentiometers. So these are wired as voltage dividers. So these are going to the right side of the potentiometer, and the outputs of the CD4017. The far side pin, the first pin of the potentiometers, are going to ground, And the output pins, which are coming through these white wires, are going through diodes all to a single point. And that is going to the control voltage of whatever voice you have going on. So, and these are adjustable to whatever desired voltage you have that controls some aspect of the circuit. In my case, I'm using a hi-hat with control voltage. So every time I can have it, in addition to being triggered, I could have it hit the hi-hat at a lower voltage or a higher voltage. And so I have these set up right now with various voltages. And so let me turn this on. Once again, we have the LFO on the left side. We have the CD4017 counting away. 3, 4, and it should be resetting. 2, 3, 4. But the outputs, which I have this wire going to the oscilloscope here from the diodes, are based on the step sequence, are controlling different voltages. So you can see different voltage levels. And this could be adjustable. So if I adjust this one, for instance, I want to make it higher voltage on the last step. And so if I wanted to control any aspect of that output signal in terms of the strength of the hit of the hi-hat, that's the way to do it. So once again, this is only a 4-step sequencer, but you can see how complicated it could get here. I've actually reused those diodes, so I took out the other part of that circuit, but with the transistor. But that is only a 4-step sequencer and for one voice. So this has got to be redone for every voice, or you can combine certain voices that are not used together that often. So either way, that is how you put together the sequencer. So that is the essence of the sequencer for a DIY drum machine, or any sequencer for that matter. And this has to be done for every individual drum voice that you use. So, I have a whole bunch of them. And so we got to get to work. But that is how the sequencer works. Thanks for watching, as always.